Hey guys, what's up? It's Mr. Mises here, and I have the second part of the L'Hopital's video. This one's going to be kind of quick. I'm just going to talk about some other indeterminate forms. This actually, I'm not quite sure if this is going to be on the AP exam for BC Calc, but it's always good to know something here on using L'Hopital's rule for these types of problems. So the following limits here are not 0 over 0 or infinity over infinity forms. This is a different type of indeterminate form. So when I plug in infinity here, for this one, I'm going to get 1 to the infinity power. Well, we all know that 1 to any power is 1, but infinity is not really a number. So 1 to infinity is another indeterminate form. All right, so this is indeterminate as well. Okay, I'm just going to write indeterminate. So 1 to the infinity power, 1 to the negative infinity power, that's indeterminate. 0 to the 0 power, well, anything to the 0 power is 1, not anything. Nothing to the 0 power, 0 to the 0 power is also indeterminate, so that's another indeterminate form. All right, infinity to the 0 power, right, because 1 over infinity would go to 0. That's also indeterminate. We can't do infinity to the 0 power. 0 to the infinity power, though, 0 to any power is just going to be 0, no matter what. So this is not indeterminate. This is not indeterminate. All right? So we can do 0 to the infinity power. We just can't do 0 to the 0 power, or infinity to the 0 power. So these other ones here, these are other indeterminate forms that we would be able to use L'Hopital's rule for. So let me show you how we use that. All right, this one here, this is one of those forms of 1 to the infinity form. So here, whenever I see a power raised to a power, I'm going to pretty much always think I'm going to use some sort of logarithm, okay? So what I'm going to do is I'm going to let y equals the limit as x approaches infinity of 1 plus 1 over x to the x. And then I'm going to take the ln of both sides. So ln y equals limit as x approaches infinity of x ln 1 plus 1 over x, right? Because when I do the ln, I can bring the x down. Okay, so this right here, this is going to be the limit as x approaches infinity of ln of 1 plus 1 over x. Remember, I have to finagle it here, x to the negative 1, so that I can get 0 over 0. So now I can do L'Hopital's rule, limit as x approaches infinity. The derivative of ln of 1 plus 1 over x is going to be 1 over, well, it's going to be the derivative of the inside, which is negative x to the negative 2, over the inside. And the derivative of the bottom is going to be negative x to the negative 2. Okay, notice that these guys cancel out. And I get limit as x approaches infinity of 1 over 1 plus 1 over x, which is just going to be 1. But remember that that was what ln of y was equal to. So then y is equal to e to the 1, which is my answer for the limit. Okay? All right, let's try a different one here. This is the form of 0 to the infinity. So I'm going to do the same thing there. I'm going to ln y is equal to the limit as x approaches infinity of 1 over x ln x. So this limit is ln x over x, which is in the form of infinity over infinity, so I can use L'Hopital's rule. So limit as x approaches infinity of 1 over x divided by 1, which is just going to be 0. And remember that ln y was equal to 0. So y equals e to the 0, which is 1. So my limit here is 1. All right? So that's how we would use L'Hopital's rule for another different kind of indeterminate form. Now let's talk about sometimes using these limits using the idea of relative growth. So basically the idea here is that some functions grow faster than other functions. Okay, in this case I'm going to show you how these functions here grow. In general, a logarithm is going to grow the slowest, all right? And then a square root grows pretty slow. A power function is going to grow next slowest, and then usually an exponential grows the fastest. So in this case, y equals 1 is going to grow the slowest because this really has no growth. This has no slope, right? It's just going straight. And then y equals ln x is going to grow pretty slow. And then y equals x, if you think about these, it grows like that. This one goes like that. Then it curves up. Then the 10th even goes faster, right? And then the 10th. And then finally, e to the x goes really, really, really fast. So if we think about this idea for relative growth rates when doing a limit, think about this here. If the limit is x approaching infinity of ln of x over e to the x plus x cubed, ln of x grows pretty slow, right? This is slow. But e to the x grows very fast. So as I go to infinity, this is going to go really slow. This is going to go very, very fast, meaning this number right here on the bottom is getting much bigger, much faster than the top one. And if this is getting bigger, faster, then really we're going to look at something like 1 over infinity, which is going to go to 0. Okay, so this is kind of just thinking about relative growth rates. Again, here, look at this. E to the x, okay, well, hold on a second. This is going to 0. So the limit as x approaches 0 from the right for e to the x, well, that's just 1. And the limit as x approaches 0 from the right for ln x looks like this. That's going to be negative infinity, which is just going to give me 0. So actually, I don't need relative growth rates in that one, but for this one, I did. Okay. All right, so that's some more L'Hopital's rule and some stuff on the relative growth rates for you all. Okay. So we'll catch you next time. Bye.